For a long time, the human brain was thought to be a finished machine. The belief was that once you reached adulthood, your neural hardware was fully assembled, locked in place, and doomed to slowly wear out over time. Up until the 1970s, this idea of the brain as a non-renewable organ was the absolute consensus. Top neuroscientists agreed that the adult brain could not generate new cells or alter its physical architecture. In the clinic, however, doctors observed severe stroke patients with permanent brain tissue damage who somehow managed to relearn how to walk and speak. Meanwhile, individuals born blind were successfully navigating physical spaces by listening to the echoes of their own clicks. If the brain's architecture couldn't change, neither of these things should be biologically possible. The answer to both mysteries is neuroplasticity. The brain is actually a living, highly dynamic network that continuously alters its physical structure and its functional properties. Because your nervous system is actively remodeling itself in response to your environment and experiences, you are never biologically locked into a permanent cognitive state. This rewiring happens through two distinct biological mechanisms. The first is structural plasticity. This is the brain's ability to physically build new anatomical connections between neurons and alter the actual density of its gray matter. We see this clearly in London taxi drivers. To get their license, they have to memorize thousands of complex city routes. MRI scans show that this intense spatial training physically increases the size of their hippocampi, the specific brain region responsible for navigation. The second mechanism is functional plasticity. Instead of building new hardware, the brain takes a specific cognitive task and moves it to an entirely different, undamaged network of neurons. This occurs most often to compensate for a serious injury. If a stroke destroys the tissue controlling your right hand, the brain can redirect that control center to a healthy homologous or corresponding area in the opposite hemisphere. Whether it is laying down new physical infrastructure or redirecting internal traffic, your nervous system acts as a survival engine, adapting its shape entirely based on the demands you place on it. You don't need to suffer an injury to trigger these changes. Consistent aerobic exercise acts as a chemical trigger, flooding your nervous system with a compound called brain-derived neurotrophic factor, or BDNF. Over several months, this chemical flood leads to measurable increases in your brain's gray matter volume, specifically expanding the areas that manage spatial memory and executive control. Skill acquisition follows the same rule. When you spend hours practicing a complex motor skill, like playing the violin, the sheer repetition forces your brain to physically expand the cortical maps dedicated to your specific finger movements. Every time you repeat a habit, your brain wraps the active neural pathways in thicker layers of myelin, or white matter. That insulation makes the signals travel faster, making the specific behavior easier to execute over time. But the true scale of this adaptability only becomes clear when we look at what happens to the brain's internal economy when an entire sensory input, like sight or hearing, is permanently severed. The cerebral cortex is highly contested territory. If a region stops receiving input, the brain initiates a process called cross-modal reassignment to ensure no cortical real estate goes to waste. In individuals born deaf, the auditory cortex sits completely dormant. Rather than leaving that tissue inactive, the brain hijacks those neurons to process peripheral visual information instead, granting them highly sensitive visual tracking. The reverse happens in blind individuals. The brain repurposes the visual cortex to process auditory data. This is how some people develop human echolocation, utilizing the sound of click echoes to precisely map physical space. Without the expected sensory signals coming in, the brain fiercely cannibalizes the abandoned neural territory to drastically enhance the surviving senses. There is a distinct catch to this extreme efficiency. Neuroplasticity is completely value neutral. It doesn't know the difference between a good habit and a destructive one. It simply hardwires whatever network gets used the most. This biological mechanism is what makes addiction so difficult to break. It is a form of structural neuroplasticity, driven entirely by chemical rewards. Looking at this animated schematic of the mesolimbic reward pathway, we see how chronic drug use floods the system with a massive surge of dopamine. Over time, this degrades and weakens synaptic connections within the nucleus accumbens, wiring the brain to compulsively prioritize drug-seeking behavior. This blind deficiency causes phantom limb syndrome, a classic example of maladaptive plasticity. When a limb is amputated, its corresponding brain map goes silent. Adjacent sensory maps quickly invade that territory. The brain misinterprets this new overlapping activity, sparking perpetual pain signals. This reveals a heavy biological reality. We are deeply vulnerable to our daily habits, our past traumas, and our environments because they all leave a permanent physical mark on our neurobiology. Every action physically sculpts the pathways inside your skull. Through the mechanics of your own biology, you are the innocent